Okay, so hello everyone. I'm John Reedy at the HDF Group, and we're going to talk about parallel computing with HDF Server. So I gave most of these same slides at Tuesday's talk with Amazon, but here I want to focus on the aspects of, first of all, review the HDF Server technology, and then I want to focus on how you do parallel computing, because it really opens a new way of doing computing with HDF. So previously in HDF, either you had a serial application or you do parallel application with a special version HDF library using MPI. And that's fine for some applications, but not a good model for others. And now we're in the new world where not only you can be reading and writing data in the cloud, but you have a new means of doing parallel workflows. And as these data sets in the cloud get ever larger, you get to a point where having one computer do your analytics is not going to cut it anymore. So you'll need to harness the ability of having multiple compute nodes doing work. So first, HDF5, it's been around. Is it 20 years now, or I forgot the exact 21 years? Okay. A lot of people don't know that NetCDF4 is actually HDF5 under the hood. And it's designed in these kind of contradictory goals of being both an archival format and a analysis ready format. By analysis ready, meaning that the intent is that you don't need to convert it to something else before you can start doing analytics over the data. And there's a long history and a rich set of tools that support HDF5, so that's all great. When it comes to the cloud, there's a certain challenge because the HDF5 library was designed for POSIX file systems. In the cloud, S3, at least for Amazon, is predominant, and object storage does not play well with POSIX. So when we originally developed the HDF server, we created a new schema to store files in a more cloud-friendly structure. So HDF server, it's a REST-based server for HDF data, our cloud-native variant of HDF. It runs as a set of containers that can be run on Kubernetes. So you're not restricted to one server computer. You can have a bunch of containers that run over a cluster of computers, and together they can support larger workloads. And it supports larger workloads, not only in terms of having more clients to connect to it, but it can accelerate single clients because a request, say for a time series extraction, gets parallelized across multiple nodes on the server. So there are cases where it's faster to access the same data selection through the server, getting data from S3, than it is to access that same data on a file on a local PC. What we're going to focus on here is the support for multiple readers and writers. So HDF5, the library, had long development for Swimmer, which was single writer, multiple readers. And because of the way the server is structured, not only is the programming model really simpler than Swimmer, also we support multiple writers as well. And I'm hoping to devote most of this time today to do a live demo of how that works. We use S3 as a data store, and we support existing HDF APIs, H5Py, H5NetCDF, Xarray, et cetera. So the idea is you have an application now that uses HDF for local computing, you can take that same application and run it in the cloud, talking to HDF server, which is talking to data stored in S3. We have Colab, which you can go right now, this very instant, and try out some of the same examples I'll be showing you. And we have a AWS Marketplace version, Key to Server. This lets you do a one-click install and set up your own server under your own account. So the schema, the idea is that for each object in a file, we store the metadata as JSON, And for each chunk, for each data set, we store that chunk as an S3 object. So here is a data set, say, imagine the heavy lines are the chunk boundaries. Each of those chunks gets stored into an S3 bucket. When users want to do a selection, say this yellow rectangle, the server will say, okay, I know I need these 6 chunks, and I'll go fetch them and put them together and return them to you. And I actually have a, I can show this, I think. If we go here, yep. Here's the bucket we use for HDF Lab, and here is one file, quote file, that we store. There's a group JSON, which is a metadata for the root group. Info JSON is just kind of some summary information for the entire file. There's a folder called D for data sets. Here we have all the data sets. And if I drill down to a data set, I see there's dataset.json, again, the metadata. And each of these, some number underscore some number, is a specific chunk. So when the server needs to read a certain chunk, it doesn't need to go to some kind of database to figure out what key it is. It can infer that chunk based on the hyperslab selection of that data set. And since it's S3, you could have any number of chunks. So we've gone up to 1 million chunks within one of these folders. Okay, so back to the presentation. So here's an example of what the JSON could look like. As you saw, all objects is keyed by the root ID, and there's subfolders for datasets and groups and data types and so on. So the schema is developed for use by HDF server, but theoretically, you could have clients that directly talk to S3 using the schema. It's just our focus so far has been on access mediated through a server. We have a bunch of new features. One I wanted to focus in on is support for traditional files stored in HDF5. So this new schema is great, but what if I happen to have a petabyte of regular HDF5 files that are stored in S3? Transmogrifying all those files to the schema would be quite labor intensive, and you'd pay for the extra storage for those modified files. So what we can do now is for read access, at least, you can directly access those HDF5 files. And how it works is we skim off the metadata, which is a small fraction of the total file size. That goes into the schema I just described, except that instead of copying those chunks, we just store a table to where the chunks live inside the file, which is stored in S3. So when the server needs to fetch a chunk, there's a little indirection, right? It goes to this table and says this chunk is in this object, and it's this offset and this size, and it can go fetch that chunk from the file, pull it in, and then process it like it would any other chunk. So Colab, as I said, it's free to use. You can try out any of the sample notebooks we have. We have sample data files and so on. This all runs on Kubernetes. So you have AWS and you have Kubernetes. Kubernetes manages containers over a cluster of computers. And you could have some containers that are doing Jupyter Hub or user notebooks. Other containers could be a key to server. And it's nice because potentially you can expand or contract the number of servers you're using to meet your current requirements. And so here's kind of a schematic. User signs in to Jupyter Hub. They get authenticated with Auth0. We spawn a container that has the user environment and an attached disk drive. And then an example, you see that we talk to HDF server to read and write HDF content on S3. So users here will make requests to a server. The server does its processing, reads and writes S3, returns data, and you have a nice environment because everything is co-located in the same data center. So rather than having data go out of Amazon through the narrow pipe, through our Wi-Fi, it can all be on this fast network. And some references. Okay, so that was pretty quick run through, but let me go now to Colab and show you how this actually works in practice. So let me see. So here I'm signed in to Colab, and let me see that. Is that readable? Maybe I can make it larger. Oops. Don't know what I did. Okay, so let's. So here's a notebook. So in the Colab, you have notebooks which are kind of like MATLAB types of things, but this notebook is running in the cloud and it's talking to the server in the cloud and talking to data in the same region. So here is a step just to make sure we have the most recent package. And if I do hsinfo, so hsinfo is one of the command line tools we have. And if I run that, it says we have the server, it's in the ready state, there's the endpoint, my username is jreedy@hdfgroup.org, I have a password, I have a home folder. Okay, so this /home/jreedy is a folder that lives on a server. And it's set up so that I have permission to write to that folder. And the server has been up for 15 hours, and my h5pyd version is 0.4.2. So h5pyd is a Python package we use in this case to talk to the server. So I load some stuff. Let's get our version. And now this data file, the /shared/NASA/nsep3 nsep3.he5 is a sample data file that we set up derived from NASA data. And I can open that. And the size of the file is about, I think it's 150 gigabytes, right? So this is cool. I can list all the data sets in this group. So you probably guessed that I didn't transfer that 150 gigabytes during the operation. We sent a request to the server, and the server queried the right object in S3, got information, and returned it to us. And if I go to one data set, it's about 32 gigabyte in size. So the shape is 7850 by 720 by 1440. So 7850 corresponds to each day of observation, 720 corresponds to changes in latitude, and 1440 to changes in longitude. So a three-dimensional data cube. I can list the attributes. I'm going to grab this fill value because that will be important later. So let's say I pick a random day here, and I can do a slice. So I can take this 3D data cube and I say I want to read the data at this particular date. And how long will that take? It took 347 milliseconds. I think if I run that again, it should be faster because we cache data on the server, right? So it goes to S3, it goes into a runtime cache. If that same data is requested again, it can be pulled from memory rather than going back to S3. And I would like to compute the mean on this slice, but we have these fill values, but I don't want to include the fill values. So I'm going to do this little NumPy operation to extract all the fill values. And now I'm going to compute the min, the max, and the mean on that. Okay, that makes sense. So apparently it's on the slice, minus 13 degrees centigrade was the coldest observation, 30 degrees centigrade was the warmest, and the mean was 17. So look at the time we took here to compute. 70 milliseconds to grab the data, 2.18 milliseconds to filter out the fill values, and 1.21 milliseconds to compute the mean. So most of our time is spent in transferring the data to our Python notebook before we do any computation. And this means that we have this opportunity, if we could run multiple processes, we could get things done faster because we could be doing multiple transfers. While some of those transfers are going on, we could be doing computation. So here, let's first do a little picture. So there's my data. That's nice. I can create a histogram and make a plot with that. So, already pretty convenient, right? I mean, we have this fairly large file in the cloud. I don't need to copy that file locally. I can just access it and pull data I need out of that file and make some plots. Okay, I'll have to hurry up. So let me do this. So if I want to calculate the mean on all the days of the file, I could do that. So here I run through 30 days and it took 2.5 seconds. But how long would it take to do the full 7,000 days? Well, it would take about 10 minutes. Well, it's not too long, right? I could, in practice, I would probably just start this and go off for a snack or coffee and come back. But this is actually small in terms of files that we expect to see in the NASA data sets. So to really be able to effectively do this analysis for larger files, you'll need to bring additional CPU power to bear. And this is what we can do here. Here's my plot. Okay. I'm going to have to spin through some of the details here, but if you have a bunch of workers, they need some way to coordinate. So I'm going to create a table that the workers will use to look for work to do, find work, do their work, and hopefully log work completed. That makes sense. So here's my table. We create the data set. And now I'm going to pull in this multi-processing package. And I'm going to find a function here, right? So while true, we're going to find a table. So I'm going to say table update where start is 0, right? So find a row in the table where there's no start value. The worker updates this table with the start time. It does its compute. When it's done, it writes back to that table, or it writes the result to this average data set, and it writes the stop time to this job scheduling table. So that's the function. And now I'll run this with 8 processes. We say go. And here you see my workers are all busily grabbing work, computing means, and writing those means to the table, to the data set. And after a bit, still working. So what's going on here is that something that'd be hard to do with the regular HDF5, because we have 16 workers and they're writing to the same data set, and they're not causing conflicts with that. Okay, so here you see like when a worker can't find any more work, it says PID 1853 signing off. Then this guy finished his work and he finished his work, and now they're all done. And that took 25 seconds in total. And there's our data sets again. I'm going to copy that table to a data frame. And now we can see the result. Okay, after all these workers ran, they all, for each day we analyze, they wrote their PID, start time and stop time. So this is nice because if you had, say, one task that died somehow, you would see that this done column wouldn't be filled in. And then you could go and rerun that particular task. But in this case, it all worked just dandy. And I can convert to a data frame and plot that. And here's the results of our analysis. So I thought it'd be fun to have compute the mean for both the northern hemisphere and southern hemisphere. And one thing I learned is that, do a plot, that the warmest temperature in the southern hemisphere is colder than the coldest temperature in the northern hemisphere. So that surprised me. So I guess maybe it's because there's more area around the Antarctic Ocean that's really cold, and that lowers the mean for the southern hemisphere. But you know, there's lots of interesting things you can do, and it's I think it's cool to provide the tools that let people who are not me, who actually understand oceanography, actually do these kind of experiments. So summing up, challenges in future work. I'd like to do the same kind of analysis for larger data sets. With larger data sets, you would need to harness multiple computers, which means, for example, running workers in a Kubernetes cluster. So there's nothing here that, I use the multiprocessing module, but there's nothing that requires those workers to be on the same physical computer, right? They are talking only through REST to other services. So you could harness 100 computers to do that. I'd like to demonstrate using other standard tools like Dask to do the parallelization. And another challenge is once your number of workers increases, you need a server to commensurately increase its capability. So we need to work out ways that the server can expand to meet the load dynamically. And then another challenge is in Colab, our costs are limited to some extent because you sign in Colab, you can only harness the power of your one container in Colab. If we enable users to launch multiple containers, then their cost per hour can go way up. You know, if I'm running 100 containers, that's a fair amount of money we spend. And so it's a bit of a challenge to think, how do you effectively constrain those costs? Okay, thank you.
Any questions?
Yeah.
Wait.
You're very good, Oksana.
Sorry, probably I have missed the point, which is like when you say HDF server, and then the file behind is one HDF file or is multiple? Or
in this case, it was one, but it could be multiple.
And what is the data model you use to manage the multiple?
That's what I was talking about here.
Is the table index?
So these are all objects in S3. So
but that is the like chunks of one file, right? One
and if I could have done the same analysis with a traditional HDF file, and in that case, here, let me go back to mine. It was. I lost my PowerPoint now. Anyway, sorry, but it was, the chunks exist within that traditional HDF file, and we just track location of those chunks within the file.
I guess I get the point, because I'm trying to think of the case where normally you get files from NASA, and then it's a whole bunch of HDFs, right? So then, like, I'm trying to parallel, like, you know, that's what our software, you know, what our software do, ArcGIS do is that we have another Mosaic dataset model to manage the whole collection of
right.
Yeah.
And I think in that case, what you do is first you list out all the files, and then you would have put those in the table, And then just like before, the worker would go to that table and say, okay, I'm looking at file XYZ and process that file and mark it done and go on. So that same kind of pattern would work for a large collection of files as well.
Okay, thank you.
All right, thanks.
Are the chunks describing? In other words, can you use a chunk all by itself without having the sort of header information?
No, the chunks are just like what you would get if you took the contents of a C array and wrote it to S3. So it's the dataset metadata that contains information like the type used by a chunk, the dimensions, and so on. So with that dataset metadata, once you have that in hand, you can read each chunk, say, into a NumPy array and process it.
All right.
All right, great, thanks.
That's it. All right, John.
Just give center. You don't need to just.
No, I need to work on some websites.
No, it's okay. QM to ULM.
Okay. Yeah. Hi, everyone. My name is Joe Lee from HDF Group. And I'm a software engineer for the HDF Group. And today I'm going to talk about Google Colaboratory for HDF-EOS. So I'm pretty sure that everybody knows about Google. And I'm also pretty sure that everyone has a Gmail account. Is there anyone who doesn't have a Gmail account? So everybody has, right? According to Google, there are 1.5 billion Gmail users. And Facebook, that I was trying to access from here, has about 2 billion people. But although you are familiar with Gmail, I think you're not familiar with the Colaboratory. So how many, we have about 17 people here. How many people heard about Colaboratory? 1, 2, yeah, 3, 4, okay, good. Yeah, according to Jupyter, 75% people know Jupyter, while 16% people know Colaboratory. And for HDF-EOS, I think, yeah, population in the Earth are not aware of this much, except for EC people. So let's see. So I'll explain what is Google Colaboratory first. So it's Google's product, and it's a free Jupyter notebook environment. And it's super easy because there's no setup required. I heard that many people complain about how difficult it is to start Jupyter Lab or Jupyter Hub or Jupyter Notebook during the ECIP session, several sessions. But Google Colab, you don't have to set up anything. And this is 100% cloud and supports both Python 2 and 3. And the best part is it provides hardware accelerator for machine learning and deep learning. So they provide GPU and even provide tensor processing unit that Google developed hardware. So for those who don't know HDF-EOS, HDF means hierarchical data format. And when I first joined the company, it was a highly difficult format. After 20 years, this is a holy data format for earth science, in my opinion. So EOS means Earth Observing System, and NASA picked HDF in 1998 as the standard format to store data collected from EOS satellite. And Terra, Aqua, and Aura are all in HDF-EOS. And it's been working really well. For last 20 years, there was no issue. Data are archived correctly, people can access. And it provides earth science friendly data types like a point, swaths, grid, although swaths and grids are mostly used. And you can access with two libraries, HDF-EOS 2 or HDF-EOS 5, and they are both based on HDF4 and HDF5, more generic libraries. So in my opinion, yeah, having this standard format is a blessing because all you have to learn is HDF, and you can access all the data. And tools are very streamlined. So for people who are not familiar with HDF-EOS, we maintain a website called hdf-eos.org, and we provide a lot of examples. So if you don't know how to use it, you can convert to your own data format like Excel or GeoTIFF or CSV, and we provide all kinds of examples how to use these data with the ArcGIS, Google Earth, Excel. We also provide complete programming examples in MATLAB, Python, and IDL, NCARS, NCL, R, C. And the best part is we provide about 281 NASA product-specific examples on the zoo. So please visit the website. So if you go to the zoo, we provide Python examples. And the way you run the code is download the HDF-EOS data from NASA. And by following our example, you modify code a little bit. For example, file name and dataset name and data processing that you want to do. And you can run the code to generate plot on the map. And traditionally, these are all done by the local computer. But nowadays, everybody talks about cloud. And the natural question is, can I run those example of Python code on the cloud? And yes, you can for Python. And my recommendation is to use Google Colab because you don't need any setup. This is simple, easy, and awesome. So if you have a Google account, please try to log in now and check it out. So where does Google Colab is? To create a new Colab notebook, you have to do a little bit more in the menu. So if you go down, Google Docs, Google Sheets, Google Slides, you'll find the Colab under the More section, and just click it. And what it does is, it will open the notebook in very familiar user interface. So it's like a Jupyter notebook, but under the Google Docs system. So you'll get the Untitled IPyNB notebook, and you'll get some notebook interface. And the good thing is, it comes with H5Py. So Google Colab has HDF5 library built in. So although there are not many HDF5 users you think, now we have 1.5 billion users who can use HDF5. So this is why I'm very excited and try to present today. But unfortunately, yeah, there's something called the PyHDF. This is for HDF4, old one, and it's not built in. But you don't have to worry about it. And also, it's missing also HDF4. So for data archive purpose, I think HDF5 is a better solution, in my opinion. Yeah. HDF4, yeah, there's a little bit users. HDF5, 1.5 billion users, right? Okay. But the thing is, you can, yeah, Colab allows you to install package using a command that starts with the bang sign. So normal command tool like a pip can be used to install PyHDF. And you can use any Linux package like using apt-get. This Colab is based on the Ubuntu, so they use apt-get as a package manager. And you can also run any Unix, standard Unix command like ls. So if you do bang ls, you can see all the file system in the Colab. And as you see, there's a TensorFlow also installed by default. So you can run any machine learning algorithm. So here's a typical packages you need to install to run our Python examples on our website. So if you follow these 1, 2, 3, 4, 5 lines of the code, it's ready to run. For data, you can also download using wget, or you can upload your file from your computer with the 2 lines of the code. So within the notebook, you can run bang wget or type this from Google Colab import files, uploaded files that upload, then it will prompt what files to upload. And the rest is the same as the Python code that we provide. So you just open the file and read the data and read the geolocation data, and the rest is this. So Colab can visualize the data, HDF-EOS data, as we demonstrate on our website. So left side is the Colab's output, and you will get the same image from our website example. So it's very simple and awesome. So how about OpenDev? OpenDev is pretty important because Colab has a limited disk space. So for big files that doesn't fit into your memory or disk space, yeah, OpenDev is the way to go. So I tested with PyDev, and it worked really well with NASA data using user registration system. And the best part is the sharing feature. So after you run the experiment, you can save a Colab to like a Google Drive and share with other people. So I have 2 Google accounts, one for personal and one for work. So 1.5 billion users are not really correct. Maybe some people have multiple accounts. Anyway, so I tried that sharing, and if I run my Colab, and if it's shared with another account, you can see the progress on the other side. So I think this can be also used as like a job screening for interview. How competent a person can write the program. You can monitor what they're doing. Also, you can save the Colab to GitHub directly. So you can share your work globally. of course, you can upload and download the existing Jupyter Notebook to Colab. And you can also see the older revision history, like an ordinary Google document. And there are more. And you know, when you write program, you always make mistakes, right? And if you make a mistake in Python code, and they catch the error messages and send a direct link to the Stack Overflow. So all you have to do is just click the link, and mostly you'll find this answer. And you can add some forms for interactive input parameters. And also you can mount Google Drive and access data from Google Sheet. Google Sheet is like Excel for Google. But there are some limits, and there are always a workaround solutions. For example, some built-in package versions are old, notably GDAL, and their GDAL is like 2.3. And I always want to use the GDAL 3.0 because GDAL 3.0 can access HDF5 using S3 interface. So you can directly access data. And for OpenDAP, I tried several modules like NetCDF, NetCDF PyDAP, but none of them work. Only PyDAP worked with the NAR source data and logging. For ordinary OpenDAP server that doesn't enable authentication, it works fine, but for NAR source data, yeah, only PyDAP worked. And there is, of course, some limit. It's like a 13 giga memory and 25 giga disk space limit. But I think it's plenty for ordinary citizen scientists. And also it can let you connect to your local Jupyter. So if you need more memory and disk space, you can use a Colab and it can talk to your local machines too. And that's my presentation, and I'll give some quick demo. Let's see. Okay. Let's go Gmail. So sign in. To save. And let's go to Google Drive. So slow. Okay. So if you go My Drive, there's a Colab notebook. They create an automatically folder like this. And as you can see, I tried with many different solutions like a PyHDF and PyTab, like this. And so, for example, if you try to open document, you can open with a Colab. So this is a subsetting data from TeraFusion product, which is like 25 gigabytes per granule. So it never fit into Colab's disk space, but OpenDAP can access without any issue and visualize data like this. And my hobby is playing golf, and what I like to do is create a map that I want to go visit like this. And you know, this location, our Tacoma has a very famous golf course called the Chambers Bay. And I visited in 2015. And do you know this Royal Portage Golf Club? Yeah, they are currently having the open golf tournament. But I want to visit there next year. So I try to use NASA Earth data to whether it's really, let's see. Yep, this is a notebook that I created today. And if you click the view in Google Maps, this location, if you click, it has a, in the URL, it tells the latitude and longitude. So before I go visit next year, I can use the search Earth data, nasa.gov. And they provide a search by the location, like a point. So all you have to do is just copy and paste this long location. And type the like OMI NO3. Oh. Let me copy from the HDF-EOS website that I talked about. So there's an example called OMI, and they provide a nice CMR link, OMNO2. So all you have to do is type OMNO2 like this with the point location. And you can specify time too, because I want to visit next August for Notre Dame Navy football game. So you can specify like August 21, 22, different date. Yeah, let's say something like this in August. Yeah. And you show like this, granules. And so what I did is I grabbed one of them for the date I want to go. And you see here, it's like last year about August 30. That's my target date. So I download the data and save into my Google Drive. You can mount the Google Drive too. And run the analysis. So this is the data that I downloaded today from Earth data. And this plot is kind of matches our 3 example. Let's see. So there's a OMI Python example. Yeah, it's a different day, but I generated the plot like this. Because as you can see, here is the Ireland region that I'm interested in. So the good thing is you can process this and visualize it. Also, you can make the data available on your Google Sheet as well using this simple code. So the result is Excel sheet like this. So this is the NASA HDF-EOS data that's imported to a spreadsheet using the Google Colab. It's 100% cloud. And from there, you can subset data based on the region of interest, which is Ireland here, 55.0, something like that. And you can use this Google Maps. And if you go like this, you can create on your places and you can save the map. So this is the OMI data near the British Open is going on. So the data is the cloud fraction. So NASA Earth Search data said it covers the Ireland, but it doesn't exactly covers that. It's very near, but it's not 100%, go to the Ireland. But what I can see here is that last year, the cloud fraction is about 1 through like a 0.80%. So whether I should play golf next year here, I think it's not a good decision because it has a lot of cloud and playing golf under the cloud is not that fun. So I better just visit the island without playing golf. I think that's the data-driven decision. And it can be all, thanks to Colab, I can make such a decision with NASA data's help. And hopefully, everybody can do like this processing. Every citizen scientist, 1.5 million users can do this and use NASA data. And everybody can benefit from data that they shared on the Google. So hopefully you can do the similar thing and enjoy the NASA data using Colab. That's it. Any question? No?
I have one question.
Okay.
Sorry, scared you.
Okay.
I speak like this. I didn't quite get the files you upload into Colab. Is it stays in the Colab environment? Is it stays on Google Drive? Does it count towards your Google Drive?
So you can do both ways. You can upload directly to the Colab environment. Also, you can upload to the Google Drive directly using the upload from computer. So both works. And if you upload your HDF5 file into Google Drive, what you have to do is mount it using the two simple line. So let's see. You see this path? It mentions the My Drive in the Google. And how this works is there's a Google all provides the example how to mount your drive. So it's not responsive, but let me go up. Yeah, there's a code for that. Oops. Yeah, I don't know why scrolling doesn't work. Yeah. Let's go up and so either way is fine. Yeah, you can just download to the Colab environment within, or just using the like this. These two lines from Google Colab import drive and drive.mount content drive. Then everything is available to Colab. So it's very neat.
Okay. Thanks, Joe.
Okay.
So Larry, get ready. Well, Joe logs off of everything. He logs in and closes all the browser tabs.
Okay. Yeah, securely. Okay.
So I'm Larry Knox. While Elena's bringing up the presentation, Alan Byrne and I run the bulk of the daily testing, regression, and continuous integration and release testing for the HDF group. And we are working to leverage the cloud in a bit of a different way than what I've been hearing the past few days, because our testing is, we only need to bring in the code and return the log, the results. We're not serving data. We're not transferring great quantities of data. We are not cloud engineers. And if you see anything dumb that we're doing or have suggestions for improvement, we certainly welcome that. We're starting from the platforms that we have in-house. We have a couple of big endian platforms, an IBM PowerPC Power 7, I think, and a SunOS 511 Spark server that are big endian machines. These allow us to test the HDF software still on big endian machines, which is becoming less of an issue probably, but HDF still supports both big and little endian. We also have several servers running a variety of Windows and CentOS Linux VMs. And we have a collection of assorted repurposed laptops and desktops that run macOS, Windows, or CentOS Linux. Our test system is made up of actually two systems. The original or the older system on Unix machines consisting of shell scripts. The newer system is the VMs run with a BuildBot master. We test 3 HDF5 versions, probably soon to be 4. HDF4 and a dozen or so applications that use these libraries. So altogether, we have more than 750 test configurations that we are running on a daily basis. Well, no. Over 2 days. It takes us 2 days to get a complete run of our test configurations. So why leverage the cloud? There are a variety of reasons. The cloud resources provide us some opportunities to expand our test coverage on distros that we don't have, and also to provide more testing time. Users often report problems with systems and distros we don't have, and the cloud gives us an opportunity to easily access those. The cost of testing in the cloud may be more economical than procuring additional servers and maintaining them. Although even in the cloud, there's some maintenance to be done. Other reasons, we can test on more distros than we can afford to have in-house. We can get these almost immediately compared to buying a server or installing software. There's no overhead for something that we may not test regularly. No system maintenance, very flexible in terms of the hardware that it's running on. And we'll discuss a little bit later, we can provide a more consistent environment for performance testing. Currently, we're testing these distributions in the AWS cloud, Amazon Linux, CentOS, Debian, Fedora, SUSE, and Ubuntu. Our BuildBot will launch spot instances, and these instances can run an HDF5 build and regression test in about a half an hour. For an instance, it costs about 2 cents an hour, or maybe less. So we can run a test configuration at about a penny. So to run all 750 would cost us $7.50 if we were to do that. We don't intend to at present, but we'll see. We've learned a few things about spot instances. They are 75% to 85% discounted in Ohio. We found out when we did the performance testing that I'll talk about, that the same instance in Ohio is 20 to 30% less costly than in Virginia. So it makes a difference, or in Oregon for that matter, makes a difference where you run your tests. Now there is the issue of whether you have the AMI in that region or not. So that's another consideration. Charges for the spot instances are based on usage for the number of seconds that you run the instance. We prefer instance types for testing that have a price history that's low and also that's stable, because spot instances, if the price goes up above what you're willing to pay, then your instance is terminated. This is less of a problem than it used to be, I think, because it appears to me, looking at the 3-month price histories, that the prices are much more stable than they used to be a couple of years ago. I was looking for, well, the instances we use have a flat curve over 3 months. It used to be there were some that were up and down every day, but I don't see those as much anymore. I suppose the cloud is maturing, there's more competition, I don't know what exactly the reason. But anyway, if you want to use a spot instance and you look at the history and it's fairly consistent, you have a better chance of not being terminated than if you pick one that is highly variable. We do have a couple of links here for test results where from all of our testing. Some are internal, some are, eventually we will get them all on the bottom link as our system matures. We intend to move all of our HDF daily tests to BuildBot and CDash to be in one system. But all of this is a work in progress. And we make mistakes. External things happen that cause problems. A fairly new thing is parallel performance testing. And the purpose of this is to track and quantify performance improvements due to code change or degradation. But when we run tests on busy systems, the results are often highly variable. So from one day to the next or one run to the next, the results change. And we are hoping with this system this H5 cluster tool, that we will get more consistent results so that we can see more immediately when performance changes. It uses Orange FS on NVMe or SSD drives in the cloud and launches a cluster with the Spot instance. It was customized for HDF5 by Stephen Varga, and that is his URL there. So this is also work in progress. He had a new version today. It had some errors, so we have to fix that. Or he has to fix that, depending on where the problem is. But it should allow us to then generate graphs of performance over time. Those are the acronyms. So again, well, I had a summary here. We're attempting to broaden our test coverage using the cloud to access resources that we don't otherwise have while minimizing any additional cost, or, well, there will be additional cost, but keeping it as low as possible. And I repeat, we are not cloud engineers, and we welcome any suggestions or improvement. Thank you. Any questions? Okay, well, feel free to stop me later if you think of anything you want to discuss. Thank you.
So hi, I'm Elena Purman. I'm with the HDF Group, working there for more than 20 years now, and playing role of we're a small company, so I'm wearing many hats, from engineering director to quality assurance to documentation to user support, and working with Larry and all group. And by the way, we kind of rushed into our presentations, being so excited. Joe probably was about golf, that we didn't acknowledge my presentation, Larry's presentation, and Joe's presentation is supported by NASA ED2 project. And we're very grateful for this opportunity to present and share our work. So I will be talking about future of HDF5 as we see it for next year, essentially this year, the end of this year and next year. I will be talking about features that are coming in the new release that is now scheduled for September, and how we plan to support our previous releases, and kind of summarize HDF5 roadmap, and if time permits, to show features that related to access to for HDF5 data in the cloud that we're releasing in our maintenance releases. So the first feature that may be of interest to this community is HDF5 references. They were introduced from the beginning of HDF5, and what a reference means in HDF5, you can store in a data set, meaning in array, in HDF5 file, a reference to another data set or to the subset of data set. So when you open data set, you read the reference, you immediately have reference to other objects stored in HDF5 file. And that feature was restricted to objects stored in the same file. So do we have any pointer?
I think if you click, go down this corner here somewhere.
Oh, okay, here it, oh, here it, oh.
Pen, and then.
I can use cursor. So I have file H5 here, and there is a array that elements of this arrays are pointers to other data sets in the file that represents an image, a graph, and another image. Or there is a data set here that points to the region of one data set, and another element points to the region of another data set. So in 1.12, we're now introducing a kind of generalization of the same concept when you may reference data from reference object that are stored in different files. So in file BH5, my elements point to data set in file H5. The same I can do with the region references. Region references are used by NetCDF. They're used very heavily by NPP files and their file structures. We introducing those references because of new feature that is coming much later, like in a year or so, for querying indexing data in HDF5 files, but we hope that you'll find those useful in applications for earth science data when you especially build collections and work with the collections of the files. Second enhancement is HDF5 reference to attributes that can be attached to the objects stored in the same file or to the objects stored in a different file. So for example, I have a data set here that points to attribute that attached to data set. It resides in the same file, or this element points to the attribute of data set that resides in another HDF5 file. Interfaces, there are new interfaces to deal with those type of references, but they easily can be converted. In 1.12, we're coming, HDF5 is always evolving to address new needs of applications, and it became clear that POSIX systems, they kind of coming to their limit in terms of performance, and there are new concepts in storage world. So we were looking how we can enhance HDF5 to access data on different storage devices, including cloud and object store. And in 1.12, a new release, we came with a new to enable storage on object store and cloud. We came with a concept of virtual object layer connectors. And we also enhanced virtual file drivers to provide this capability. Those connectors are developed by us, and they're developed by our collaborators. They reside in the open source in the Bitbucket repository that we supported. If you are interested, there is a link. You can go and see the connectors we have. The one that we will be releasing with 1.12 is a RESTful, and you'll see on next slide how it will work. And this is used by, can be used with in conjunction with HSDS. So the new architecture, on this plot you see shaded objects represent the components that are available in the current releases. So whatever is not shaded is coming in the new release. So on the top of our library there are HDF5 APIs, and there is a thin layer of wall layer that intercepts HDF5 calls and can redirect it through the wall connector to custom implementation of putting data into storage, or it goes through the wall connectors, so-called pass-through connectors that go into HDF5 core library and then result in calling virtual file drivers that essentially operate with offsets and sizes of bytes and put them in the storage. And we use both principles of virtual file drivers and connectors to talk to cloud and to object store. So what it means for HDF5, new capabilities for HDF5 applications. First of all, there are minor change, and I hope I'll show you what minor change is, or absolutely no changes to applications are required to store data in the cloud or object store. So for example, if application it goes through HDF5 APIs, it uses S3 VFD that will be released in 1.12, and it also will be released in releases of 1.10, and we even backporting it 1.8 because it's just infrastructure that was available in the library for quite some time. S3 VFD translates offsets and sizes of the requests that go into the POSIX system into get ranges request and access cloud HDF5 file in cloud. When we go through the wall layer, we use RESTful, and which is open source. It talks to open source HDS that John presented, highly scalable data server, and puts data in the cloud. You can see here that I'm talking just HDF5 application. I'm not talking about specific Python application or something. It works with any application that sits on top of HDF5 library. So what does it mean for HDF5 ecosystem? If you have MATLAB that uses HDF5 library that has S3 VFD, or it is new version that is coming sometime, new version of MATLAB that will be using new version of HDF5 library, it can use open source RESTful and highly scalable server and talk to cloud. So for a user who uses tools like HDFU, H5Dump, Panoply, GDAL, Scala, H5Py, there is no absolutely changes if they use the library with those new features. I kind of talked to this slide already. Tools were modified to now they understand that there is a new driver, and you can specify with the option read only S3 where to find your file, and then tool works exactly the same way if you were accessing file on the local system. If you work with the application, the only change you may want to do if you do not want to use environment variable that will provide to select the driver, you can set call to tell library to open the file with the S3 driver using specific call like setfapl RO3. I always read it RO3. Credentials can be passed via parameters to this function. If you are setting environment variable, credentials can be passed through configuration file that by default will be found on the system. And I will leave them after the presentation. Also in 1.12 release, we're releasing driver based on the same principle as S3 driver for Hadoop distributed file system. Once again, you set environment variable or use specific call to tell library to open the file that it resides on Hadoop file system, and then you can access HDF5 file on Hadoop file system with the tools that you usually use by accessing file on the POSIX file system. Once again, it doesn't matter if it's netcdf4 or HDF5 file, library will read it, and netcdf4 library will read it. Last year, we announced that we are dropping support for HDF5.1.8, but what we found that performance, because we're releasing new major release 1.12, we found that performance for some use cases is unacceptable, and we have to fix performance of 1.10 and 1.12 for those use cases so our users can safely move from HDF5.1.8. So we will be supporting 1.8, and we will be applying security patches. We'll continue fixing critical bugs, and we will work on performance improvements that are kind of applicable across all releases. But at this point, as I mentioned, 1.8 for some use cases performs better than our later releases. And this is why it's so important for us to work and really pay attention to how our performance test suite performs and it complete. And we have special infrastructure that Larry mentioned, really to catch up small changes in the library performance so we can address issues as we go and not several years after. This is a HDF5 roadmap. Probably you cannot read that. Slides will be available. I just, in general, will tell that we will have 1.8 release in fall 2019, around November time, and then we hope it will be our last release of 1.8 in 2020. For 1.10 series, we have regular releases that coming in November and May, and we'll have on this schedule. And as I mentioned, we will most of our focus will be on performance and bringing 110 performance to level of 1.8 or even better. And with HDF 112, we releasing new features that will be backported, like drivers backported to 110, but 112 will have wall connectors, and focus will be on performance of 112, on supplying wall connectors and dynamically loaded VFDs that we're working on with 112. And we will continue enhancing with the new features like mirror VFD, provenance VFD. It's VFDs that we are trying to create, we're creating for synchrotron community to pass data from one system to another. It's kind of streaming data. And also provenance VFD will allow you to create several versions of HDF5 file, and don't worry that you can replay your history, how file was modified. Since it's outside the library, it's really nice mechanism to introduce new features without library modification. And if you want to learn more, we're starting webinars, and our first webinar will be on Wednesday, July 31st, how you move HDF5 application from one major release to another. And then we'll be talking about new features that are coming in our releases. There will be a few tutorials that we will be giving by the end of the year. And if you are interested, see our announcements on HDF forum and our website. And if there are any questions, I may give you a demo of S3 driver, how easily it works, if it works for me. Yes.
You talked about the REST vol, and then you talked about the S3 VFD, and then you talked about the HSDS VFD. And they all seem to be ways to talk to the cloud.
Yes.
Why three different things? What's, you know, I don't, if you explained the difference, I didn't catch it.
I didn't.
I mean, architecturally, I can see
yeah,
the difference.
I didn't explain the difference, and they are really applicable for two different, I would say, use cases. So S3 VFD allows you to talk to HDF5 file in object store in cloud as is, and if you are a user running your own application from C, Fortran, Python, R program. It also allows tools that users use on their desktop immediately talk to cloud without any intermediate agent like server, HSDS server. There are downside of this approach because it is not scalable, it is slow, and you will see it is not very fast way to access data in S3, but it is a way, and for many users it probably enough if they want to look at the file and get some metadata from the file and just visualize some regions. Well, you do more analysis, this probably is not, it probably will be expensive. We do not know the cost, and John may talk to this more. And this where HSDS come into place because it's designed to scale, while S3 driver, it's known it will not scale. It can be optimized, it can perform, and this is in works, but it will not scale. So HSDS solution is scalable solution. Once again, it provides access from any application that it's not only Python, it's C, Fortran, R, Scala, some other languages. And of course, OpenDev works with both solutions.
There is. Right, there was S3 VFD, there's a REST vol, and what was the third one? But HSDS is the server that the REST vol talks to.
So,
right?
no, Hadoop is different, right?
Yeah, and there was a Hadoop.
Hadoop.
Its own thing, right? Correct. REST vol is a plugin
Right.
for the client side of the server.
Right.
HSDS VFD is needed for the REST call.
The HS,
It's
no,
part of the
there's
REST
no
call.
HSDS VFD. There's the RESTful. HDFS VFD.
Oh, it's HDFS.
Yes.
Oh, sorry.
Right,
A little
so-
confusion of
So a RESTful is needed to talk to HSDS, to talk to cloud.
Yeah, I think you're thinking of the Hadoop one, which you had.
And
next
there
slide.
is a Hadoop one that I mentioned on the slide, but I didn't put, so I will not polluting here. Right, roadmap, it is HDFS, Hadoop file system, VFD. Right. So it's just another file driver that allows you to talk to HDF5 file on Hadoop system.
Anyway, I want to say two other things. Is one, I think it's very hard to say definitively how applications will work either with the S3 VFD or the RESTful or compared to just copying the file locally. I think you really have to run your application and investigate which work best for that application.
And for different applications, it will be different.
Yes,
Yes,
exactly.
yes. I was going to show you demo, but I lost once again connection. So, and I have 3 minutes. So, lady, if you give me once again ID, and you will see how quickly, for
I have
example.
another question.
Yeah.
Can you explain the difference between a vol and a VFD?
So there are two, okay, John, go ahead.
So the VFD operates at a lower level of a library. VFD basically goes in way low where you have the equivalent of a POSIX read or write command. And it can replace that POSIX call with something else. In the case of the S3 VFD, it's replacing that with the S3 range get call. The vol, by contrast, is a higher level where it's basically mapping to the HDF5 API layer and doing potentially an entirely different implementation of the library. So for example, if you are creating a group, in the vol layer, that would be one request doing one thing. But in the VFD level, that might be many requests where they're writing metadata in different locations in the file and so on.
Thank you.
Good. Questions and report?
I'd like to ask the HDF reference, the data model.
Mhm.
So, I would guess that you will have metadata and describe the, label that is HDF reference, and so that user will know, like the software will know, what the type of HDF is, and then open with the right software.
In HDF5, reference is defined by data type that HDF5 provide. So when you describe, there are APIs to create the reference. And when you create, you say, I'm creating reference to the data set or reference to the group. And HDF5 returns its internal representation of that reference. And that representation, that data within this representation can be stored in HDF5 using specified data type called reference data type. So when you open with HDF5 APIs, a data set with references, you first can discover what kind of references is it. Is it to objects or to subsets or to attributes or to external attribute, and then library will resolve that reference and give you the object that it points to.
Okay, so another question is there any, do you know any organizations or satellite or whatever they want to use this reference or?
Yes, NPP files, if you look at GPSS files or NPP files, they use references to describe their data products. And those will be stored in the HDF5 file. And our browser tool, HDF-EOS, has an option to work in user-friendly manner, work with those references, showing that element points to this data set or to this particular subset, which corresponds to granular when you have aggregated data sets in NPP files.
Okay.
And we can show you, I have example, and probably Larry has, yeah. It's a very powerful mechanism in HDF5 to connect data. Yes, and it will be used in indexing that will provide with HDF5. So here, if you don't mind, I have my message directory with the two examples. But first, I have the command. I have file in Amazon East. You see here the specification. So I can use H5 dump, regular H5 dump that installed on my system, and print data from that data set. So I can just try, and there will be small delay that it goes and reads metadata, and then printf takes over. So really not much. I'm accessing now with the regular online tool, H5 dump, to print data. So you see the speed is really, you cannot make the difference, see the difference between local access and the only change I have to do in the program, I have two programs that visit data set. Here I can visit this one and print metadata of this data set, or I can access a program here to access it in the cloud. And the only difference, let's see if I have history, grab div. I just was doing a difference between two files. You will see it is only one call. It is called to describe metadata that I should, credentials that I should pass to read-only VFD, and then call to set up access to the file through this call. The rest of the program stays the same. So if you want to see the program, it is really very simple. So this is main program that initializes the data, then creates a property ID or property list that I set to use S3 VFD, and then I open the file and visit objects in the file, and I can use H5CC script to compile the program as I do when I work with them on local disk, the same, no difference in my workflow. Now it created .a file and I'm running it. So now I will be accessing data in the cloud, printing out to my screen on this computer objects found in the file. And this is especially bad use case for S3 driver and HDF5 because we're pulling not some portion of data that goes and grabs data and prints it. We're going through all files, scanning all file, reading every object and analyzing it as a data set or it's a group and printing on the screen. So it's metadata rich, and we're going using many requests going to cloud. And as you see, speed is not bad at all. And especially we're on the west, it's in the east, it's working. So, any questions? So thank you very much.
Yeah, thank you. And